Thank you. First out, I would like to thank the organizers, particularly Alex, for inviting me, for putting together this very nice workshop. I'm enjoying it so far very much. The title of my talk is Exotic Landau Levels. And this is the first talk in a short session about quantum magnetism. Unfortunately, I have only the normal time slot, so I'm not able to give a long, extensive introduction to quantum magnetism. Nonetheless, there will be a short introduction about Kitaev spin physics, to give you an idea why we care about this and why this is interesting physics. I will come to the main point and show you that what these Majorana Landau levels are and why we need them, besides that there's the cool thing. And then if I have time left, two other topics which are closely related to that, which might be then more accessible to people working in the topological insulator or graphene community. So let me acknowledge my co-workers. Matthias Wolter from Dresden, I'm a student in Goethe, Swiss from Utrecht, Daniel Rovers from San Diego, and then the Minnesota people, and Johannes Knolle from Cambridge. So let me jump right into one of the most or hottest topics of frustrated magnetism, quantum spin liquids. And so this is a very elusive state of matter, which I try to define in the following. So we assume that we have a crystal, we have local moments, so spin physics, and in such a system, in contrast to what we usually expect, no magnetism is present. Or in other words, think about a system which has undergone a metal to insulator transition driven by interactions, but no order, no long-range order occurs down to low temperatures. So no spontaneous symmetry breaking, and this happens due to strong quantum fluctuations. Let me emphasize right away that this absence of order implies that there are also absence of features in the observables, which makes it notoriously difficult to look for such a state of matter, to detect it experimentally. Now, how is this possible at all that something like that exists? And so kind of one of the mechanisms which allows for this frustration. So the simplest picture you can draw, you might have seen this, is a triangle where you have Ising spins. That means they can either point upwards or downwards. And for antiferromagnetic exchange, they want to align antiparallel. And now if you try to make them all align antiparallel, you see that one of them kind of has a problem, and this is what they call frustration. And then the formal solution is that there's a degeneracy between this third spin pointing upward and downwards. And then you see, if you do this more careful, you can permute this around in actually 6 states, the degeneracy of 6 classical spin configurations. If you go for a larger lattice, then you will see that actually there are more and more degenerate states, and this extensive degeneracy is a hallmark of frustration. In fact, if you look for this Ising model in triangulars, you see that at the end a residual entropy. For the younger people in the audience, they may wonder how this started, why people think about this. And I think this goes all back to Phil Anderson, who proposed a long time ago, the context of his RVB story, that if you take such a spin liquid and you dope it, the emerging superconducting state will probably have the same magnetism as the high temperature cuprate superconductors. And that kind of was the starting point for spin liquids. Today, more than 30 years later, there are other reasons, independent of high DC to think about spin liquids. And this is due to the rich phenomenology of spin liquids. For instance, one of the key features is electron fractionalization. And electron fractionalization means that the elementary excitation of a system carry different quantum numbers than the original constituent of the system, the electrons. So the most prominent example probably is the fraction quantum Hall effect, where the elementary excitations are quasi-holes with charge E/3, the case of a Lufkin state, for instance, while the electrons, of course, have charge E. Now, to give you an idea what it means for a quantum magnet, let me draw this kind of simple cartoon picture for a one-dimensional classical Néel state. And if you wonder what the excitation might be, you can flip one spin, as shown here. But then this is not the excitation, because if you apply the Hamiltonian, you see that kind of this goes away. Instead of these two objects emerge here, and that's what we call a spin 1/2 spin-on. To give you a brief idea why this is fractionalization, it's easy to see. First of all, consider that there's every side a spin, it means there's a charge, so there's no charge defect. In contrast, if you look at the spin configuration, you see that this up-down order is kind of is violated here and there. So if you wish, there's like a missing spin down. And this missing spin down is exactly the spin 1/2 spin-on. So this simple cartoon gives you an idea that fractionalization can occur And in 2 dimensions, similar things happen. They're more complicated. You might not be able to draw a cartoon, but the physics is kind of similarly interesting. And in some of these cases, these excitations then even obey this non-abelian exchange statistics, and this is believed in certain situations to allow as key elements of future topological quantum computation. Well, now going back from this rather abstract consideration, what does it mean for an experiment? I told you that there's actually hardly any signatures for spin liquids, with one major exception. This fractionalization leads in certain inelastic particle scattering to signatures, as shown here in inelastic Newton scattering. So what you essentially see here, in contrast to a well-defined mode, like for a macron, where you have energy-momentum relation, here, since the kind of spin fractionalizes into 2 spin-ons, kind of only the total momentum is fixed while the relative momentum is free. That allows them to kind of occupy, instead of a mode, a whole continuum. And this kind of broad continuum is something you can observe, which is mainly the only feature we have. Here's the experiment. That's theory. Very nice agreement. Okay. So now let me switch to 2 dimensions, where things are a bit more complicated. Fortunately, there's kind of one major exception. Due to Alexei Kitaev, we have an exactly solvable spin Hamiltonian. This is like a miracle, because usually 2 dimensions, many-body Hamiltonians are not exactly solvable. And this one even features a spin liquid ground state. I will explain later that this is even for experimentalists interesting, because this is believed to be realized in a class of transition metal oxides. So here in this Kitaev model, so don't confuse this with the Kitaev chain, with the Majorana chain. This is really different. It's another famous paper of Kitaev. In this Kitaev honeycomb model, the physical spin 1/2, they fractionalize into dispersive Majorana fermions, or spinons, and get static Ising fluxes, or Wisons. And very briefly, it's a highly anisotropic spin Hamiltonian. You see in the honeycomb that is these red links, only some of these links have these sigma x Ising interaction, while the green links have these sigma y interactions, and the blue links have these sigma c interactions. It's highly spin anisotropic due to strong spin-orbit coupling. I don't have time to explain how to solve this, but I want to just flash one slide to give you an idea of the beauty of this model, why it can't be solved exactly. Essentially, the main idea is that you can define these flux operators, or Wilson loop operators, which is a product of 6 Pauli matrices. So for every placket on the honeycomb, that is, you can define such an operator consisting of 6 Pauli matrices, where different colors correspond to different Pauli matrices. And now it's easy to see that kind of the placket operator here commutes with its neighboring, and with all the other placket operators, it also does commute with the Hamiltonian, and so you end up with a set of conserved quantities. And that's essentially the many-body Hamiltonian decomposes into many blocks, and which we can solve individually. Now at the end, once you have solved the model, which would take another 4 minutes, I don't have, you essentially end up, and the beauty is that you can nicely see that you're left with these 3 dispersive Majorana fermions on honeycomb lattice, which are coupled to a static emergent gauge field. And since we have 3 Majorana fermions on honeycomb lattice, you get something you know from graphene, and since the Majorana fermions are real compared to complex canonical fermions, so it looks like half the excitation spectrum of graphene. So this is the spin liquid of Kitaev. But now the major problem, let me point this out right away. As for the spin chain, this is excitation spectrum by Majorana fermions. So you can't probe this with, say, an STM, so you wouldn't see anything, just see a boring mod insulator. So instead, again, you have to look for some inelastic particle-particle scattering. And so the quantity to go for is, for instance, the dynamical spin correlation functions, or the structure factor. So this is pioneering work by Johannes Knolle and co-workers. And here now it becomes really crucial that we have fractionalization in the system. A normal correlation function is just that you have 2 operators, you sandwich. But now what happens is, since these spins fractionalize into Majorana fermions and Ising fluxes, it's really like having a correlation function, but with fluxes to the right and to the left. You have these pi fluxes next to the bond you're measuring. That happens automatically, dynamically in the system. It's like having a bond impurity, or if you wish, you can think of a quantum quench for the matter Majorana fermions. In any case, this can be solved exactly for the pure Kitaev model, and the result is shown here. You see the structure factor in the preon zone, and again, this completely featureless, hardly any dispersive behavior, and similar to the spin chain. So this is essentially the signature the Kitaev spin liquid gives us. Okay, so this is interesting. And now for the experimental audience, or the experimentalists in the audience, let me briefly point out why this is relevant to materials. So it goes essentially back to work by George Thackeray and Vinod Kaliolin, who realized that in certain transition metal oxide, as in this iridates, this type of spin interactions, as exotic as it might look, is indeed realized. And briefly, the idea is that so you see two iridium atoms surrounded by this oxygen octahedra, and then in addition to the generic Heisenberg exchange, it happens that you have super exchange via this oxygen. So these big fat dots are the iridium atoms, this is oxygen. You see there's super exchange along this path and along this path. If there's exactly 90-degree angle, it turns out that you get destructive interference for these two paths in the hopping matrix. Heisenberg connections cancel out, and what you're left with is indeed Kitaev exchange. So this super exchange giving rise to Kitaev, plus the ordinary Heisenberg exchange gives rise to what we call the Kitaev-Heisenberg model. This has been claimed to be realized. Today, it started really a lot of experimental interest and efforts. Many people have worked on this, in particular, Philip Gegenwart in the audience has contributed a lot. And today we know a bunch of materials who fall this category, and they're also, in addition to Kitaev exchange, there are other more generic spin exchange present. But unfortunately, all these materials have in common that so far at low temperatures they order magnetically. Nonetheless, there's a strong belief that one is very close to spin liquid phases, and that right now people try with pressure, strain, magnetic fields to push these materials in the spin liquid phase. We might hear more about this in the next talk. One thing I want to point out here. So this is Newton scattering data by the Nagler group for ruthenium trichloride, and this material is orders at lowest temperatures in a zigzag state. Now the interesting thing is that if you do a spin wave theory for around the classical zigzag state, you can essentially reproduce these features here, so everything except that here. But if you take a pure Kitaev spin liquid, you can reproduce this kind of feature here. That's made them believe, or that's why they have the claim that they're the proximity to the Kitaev spin liquid. So very close by. But you see that this is hardly evident or really a smoking gun proof that this is close to a spin liquid. So it would be very nice if you could add something to the model such that you get more structure into this. And this brings me to the main part of this talk. We want to do something to this neutron, to the measurement of this, not to the measurement, but to this model such that it shows more structure in the structure spectrum. So we want to keep the exact solvability, but manipulate the Hamiltonian. And there's one loophole where you can do this. Essentially, you can manipulate all these magnetic exchange constants on the lattice in real space, and that allows us to apply a strain field to this spin liquid. So this brings me immediately to the physics of graphene and carbon nanotubes. There it is known that a two-dimensional strain field applied to Dirac fermions acts as an effective vector potential. So essentially, the components of the strain field enter here in the vector potential, and you see a uniaxial uniform strain gives rise to zero magnetic field. Then it was Paco Guinea and co-workers who realized or figured out that what is today called triaxial strain gives rise to approximately a constant magnetic field. So this is in polar coordinate, gives rise to a constant magnetic field. One peculiarity I want to point out. So this if you go in a honeycomb lattice at the valley k, like here, you have plus vector potential, but in the other valley k prime, you have the negative vector potential. It's really like you have this situation. It's a bit like quantum spin Hall effect, but now with valleys of opposite sign. That's why the whole thing is time inverse invariant. But other than that, it should work like a normal magnetic field. In the case of graphene, you can test this, take a graphene disk, apply forces as shown here, apply to the circumference of this disk, and you do this and you do molecular dynamic simulations in the local density states. You will indeed observe Landau levels when you turn on strain. There were even experiments later on. People looked at some graphene films on platinum substrates, and if you cool this down, these nanobubbles sometimes form spontaneously, and some of them have this peculiar shape you need, and then STM measurements reveal a spectrum which looks similar to that of Landau levels. And the second experiment by Hari Manoharan's group, which is even more impressive, I believe, they used their designer graphene approach, and they also tried to mimic this distortion of the lattice due to strain, as shown here, and then measuring with STM, you see nicely these Landau levels in the local density of states. So for graphene, that worked. And now we want to adopt this idea and apply it to the Kitaev model. Essentially, we can now adjust all the magnetic couplings such that we have this strain field. And if you want to think of distortion of the lattice, just imagine a honeycomb lattice having the shape of a hexagon. And now we apply strain. For the sake of illustration, a very strong strain, like 66%, it would look like this. And now we are ready to compute density of states. This is for the case without strain, like for the normal honeycomb, for the Dirac fermions. And then if you turn on strain, you see these kind of isolated, highly occupied states emerge in the density of states. And to further analyze this, we can remind ourselves how the quantum Hall effect on the honeycomb lattice works. The energy dependence of the Landau level index goes with the square root of n. So if you take the energy position, it nicely falls into the square root. So really they have something like Landau levels. Since we started with spin liquid with Majorana fermions, now this excitation spectrum has this form of Landau levels. We indeed end up with Majorana Landau levels. So I've shown this slide before, and now we want to compare if you're able to compute such a quantity, if you can see these Landau levels in the structure factor. So over here, without strain, we can nicely reproduce the result from the literature. Now if we turn on strain, this kind of broad peak melts away, and instead we get a sharp sequence of isolated delta peaks. So if you're looking for a smoking gun signature experiment, here you have it. Okay, so of course everyone thinks now, well, you have Landau levels and density of states. Now you get it also in the structure factor. That fits very well. But it turns out that this is actually not directed at Landau levels. What you see is a bit more complicated and more interesting. And I want to briefly explain this. And now kind of the fact of your fractionalization is kind of really crucial. I told you that we're not just measuring a correlation function, but these two fluxes are in a system that acts like a bond impurity on the bond you're measuring. So the question is, what happens to this Landau level spectral structure if you add one bond impurity? It's a very simple, basic question. And the answer is kind of non-trivial. It turns out that in every single gap, in each Landau level gap, you get a single particle bound state. And precisely these Majorana fermion bound states have the largest matrix element in the correlator, giving rise to these peaks. Let me substantiate what I just said. So here we see the structure factor, and these peaks, you see, if you look at the ground state, they're exactly pointing inside the gap. So all these peaks are kind of going inside the gap. But if you look in this density of states where you have these bond impurity, the two fluxes, you see that exactly where the peaks are, you have highly occupied states. And these are exactly these bound states I was talking about. And if you look at the wave function, you see that indeed where you do the measurement, you have a highly localized state. This is an extremely robust mechanism because of these bound states, which are kind of surviving. Whatever you do to this spectrum, you get this nice signature in the structure factor. Okay. Let me skip that part and tell you a bit more about Landau levels. Probably most haven't heard about yet. So what I was always what I never liked about this is, so what I didn't tell you is this is the local density of states for a large system with about 15,000 sites. So there's no finite size effects for sure. Nonetheless, we all agree that this doesn't look as perfect as you're used to from textbooks, when you think about Landau levels, right? So then it might be clear, or you might think that this is because of the low energy behavior where this kind of comparison with the vector potential is true. However, we understood after a while that the nonlinearity of the strain field is causing all that. So essentially, you can kind of manipulate this kind of strain field by the distortion, C bar, or by the magnetic elastic coupling, or Grüneisen parameter, beta here. And you can play with them while keeping the same strain strength. And I want to show you how you can reduce nonlinearities of the strain field and getting something much nicer. So this is not the local, but the total density of states, where you hardly see any Landau levels anymore. And now let me reduce these nonlinearities. And you see the full density of states immediately has very nice Landau levels and a whole long or wide region of the spectrum here. And if we for academic purposes go further, make the strain field even less nonlinear, make it perfectly linear actually, what we get is something very surprising. A density of states consisting only of delta peaks, so we get perfectly flat Landau levels with no dispersive behavior whatsoever. Let me zoom into this spectral plot. So this is just a diagonalization of free fermions. Has not necessarily to do with some spin liquid physics anymore. It would work for graphene or so as well. You see that it's really perfectly degenerate even at the band edge. And you also see that the degeneracy is increasing once you approach 0. Now what happened here is essentially that by making the strain field linear, that kind of all bonds in the same direction, like this bond, this bond, this bond, this bond, they all have the same strength. Now you can scale them to be integers, then you see that each row is kind of reduced by 1. So if you say you have a hopping of 3, of 2, of 1, and there's a line of bonds where the hopping is exactly 0. So it means automatically this kind of strain field cuts out a certain geometry, which is in that case a triangle. And if you now play for, say, for academic purpose, for fun, around with this triangle, and you do such a tight binding model where you have this hopping reflecting this linearity, what you get is exactly this perfect spectra. Now, usually spectral values are just random rational numbers, but here it turns out that these numbers are all square roots of integers. And if you see these numbers, it doesn't take long to realize that you can nicely write this in a closed form like this. If you square root of these numbers, where n squared is just the number of sites, and small n is essentially index, which labels all these states corresponding to the degeneracy of these states. So this is an exact statement. It's quite surprising, but at least now you get perfect Landau levels. Okay, usually Landau levels are associated with quantum Hall effect, and you all know that for fundamental reasons, quantum Hall effect only exists in even space dimensions. Now such a strain field, of course, can probably also apply in other dimensions. So the question is, can we get this in higher dimensions? And in fact, we can. So if you look for a diamond lattice in 3D, that would correspond to tetraxial strain in a diamond lattice, you get also in kind of this idealized form a perfect flat Landau level spectrum, even in 3 dimensions. And again, you can write this in the closed form, and you can prove all that. And of course, once you have it 2 and 3 dimensions, you can write it in d dimensions. And this is then what we call hyperdiamond lattices. And you can again write this in this nice closed form. Also can give the degeneracies and all the details. Okay, so with that, I'm at the end of my talk. And I want to thank you for your attention.